Hi, I'm Dr. Hay. I'd like to show you an energy conservation problem that involves all kinds of energy that we know of so far: kinetic energy, potential energy, spring potential energy, and I'll show you how to use this fundamental equation. The work done by the non-conservative forces is responsible for a change in mechanical energy of a system. So here we have a block beginning on this wild track here. It's going to have a mass m and a velocity v, and it's going to travel around a loop-de-loop and then up a really steep hill and compress a spring. And maybe we're being asked in the problem, what is the compression of the spring? How far does the spring compress? Okay, we can solve this problem with energy conservation. If we had friction in the system, or air resistance, which we're going to ignore air resistance, and we're going to assume the track is frictionless, but if we were given friction, for example, if we were told that there's some patch that has friction in it, then some energy would be taken out of the system. Some mechanical energy would be taken out by the work done by friction. It would basically slow it down as it's going through here. And we'd have to consider the work done by that frictional force. But let's assume for now that we have kinetic energy. Initial, it's going to take its course here. It's going to gain potential energy, that's gravitational potential. And then it's going to compress a spring, and now it has spring potential energy. And at that very moment when it compresses the spring, before it comes back down, it is holding still, which means at that moment it has no kinetic energy. Okay, so our equation says that the work done by the non-conservative forces here, the only force that we know of that's non-conservative at this point is friction, and there's no friction here, so that's 0, is equal to the energy final minus the energy initial. So the final energy for this occurrence, it doesn't matter what it does on its way through, only if it interacted with a frictional force, which it doesn't. So the final state of energy is mgh, because it's up a height h, and 1/2 kx squared. We would have to know the spring constant k. Okay, the final energy is the spring potential So I've written my final energy here. Now I need to subtract the initial energy. Now I've got the initial energy of the system. It had no gravitational potential energy down here and no spring potential energy. So this is the final energy minus the initial energy is equal to nothing because no energy is lost in this system. So now I've got everything I need, one equation with one unknown, and the unknown in this case is my spring displacement, the distance that it compresses the spring. So I could solve for x here. So I've solved for the compression of the spring, and that's how you use energy conservation, this fundamental equation, to solve a problem that has a bunch of moving parts. It doesn't matter what it did in between. What mattered was the initial energy, the final energy, and any work done by friction on its way through.